Ever try explaining time to a 5-year-old?
Ugh.
It's like, it's like trying to nail jelly to a tree. You quickly realize we just take it for granted. But how do you actually measure something as slippery as time? Especially when you're talking it's like crazy fast stuff or billions of years.
You're right. It's more than just clocks and calendars. That's why we're diving into the Feynman lectures on physics, chapter 5, time and distance.
Feynman. Now, there was a guy who could explain anything, right? So time and distance. What's he got for us?
Well, first thing, he flips the whole idea of defining time on its head. He says, forget dictionaries. Physics is about what we observe, what we can measure.
Okay, so less what is time
Mhm.
and more how do we measure it? I like that.
Exactly. And when you think about how we measure time, it often comes down to finding patterns, things that repeat reliably, like a day, for instance.
Sunrise,
Yeah.
sunset, simple, right?
Feynman points out, even a day can be tricky if you rely just on what you see. Like, how much longer do summer days feel compared to winter?
Oh, for sure. Summer days, you're out late, barbecue, time flies differently.
Exactly. He uses the example of an hourglass. Imagine measuring a day by how many times you flip it.
So, one periodic thing, the sand, to measure another, the day-night cycle.
Right. But if you kept track, you'd notice inconsistencies. Some days would have more hours by the hourglass. Like some days the internet's just slow, same 24 hours, but
It drags. So, the hourglass isn't wrong, it's just. The Earth's rotation isn't perfectly matched to how fast that sand falls, like a ruler where the inches keep changing. No wonder time's so tricky.
and that's why we've come up with more precise ways to measure those smaller bits of time within a day. Sundials, mechanical clocks then, Galileo with his pendulums.
Pendulums. Galileo noticed that swing back and forth was remarkably consistent, like a grandfather clock, mesmerizing and accurate.
And revolutionary because it meant more precise subdivisions of time. Fractions of an hour accurately led to the pendulum clock. Who knew a swinging weight could be so precise?
It's like taking those natural rhythms, oscillations, vibrations, and using them to break time down. Ingenuity. But even pendulums have their limits. For even tinier slices of time, we needed something way faster.
Absolutely, and that's where electronics come in. Remember those natural rhythms? Electronics opened a whole new world.
I mean, like electronic oscillators. Always sounded complicated.
Think of them as super fast electrical pendulums, vibrating insanely quickly, thousands, millions, even billions of cycles per second. We're talking tiny, tiny fractions of time.
Wow, from a swinging weight to an oscillating electrical current. But how do you even calibrate something that fast? Are we talking physicists with stopwatches counting blips on an oscilloscope?
Huh, that's a funny image. Luckily, no. They used something called an electron beam oscilloscope. It's like a microscope for time, lets them actually see those super fast oscillations on a screen.
So they slowed time down enough to see it, like those nature documentaries where a hummingbird's wings freeze.
Exactly. And that meant we could measure time in billionths of a second, even trillionths. And with lasers, we're down to femtoseconds, a thousandth of a trillionth of a second.
Okay, I officially need a minute to process that.
Right.
But this is more than just faster clocks, right? There's a bigger picture here.
You got it. It shows how physicists get creative when they can't measure something directly. Like, with ridiculously short periods, they relate them to things they can measure. Distance, speed.
That is fascinating. Got an example. Because honestly, picturing a trillionth of a second, let alone measuring it.
Feynman uses the pi meson. It's a subatomic particle, crazy short lifespan, decays so fast you can't measure directly.
Poof. Gone in a flash of, well, whatever subatomic particles are made of.
Right. They knew its speed, near light speed, and they could measure the tiny distance it traveled before decaying.
So they knew how fast, how far, and from that, they worked out how long it existed.
That's amazing. It's like figuring out how long a soap bubble lasts based on how far the wind blows it before it pops.
Exactly. And that's how they found the pi meson's lifespan, about 10, 16 seconds. A millionth of a billionth of a second. Mind officially blown. They made a clock out of a near light speed particle. Makes you wonder, how small can we measure? What's happening in those tiny slices of time? But hey, I think we've gone far enough down the tiny end of the scale for now. How about we zoom out and look at the opposite end where time stretches out for eons? Okay, from the nearly immeasurable to the unimaginably ancient. It's wild we can learn so much from those tiny bits of time, but what of the stuff that makes human history look like a blink? How do you even measure those time scales?
It's a whole different challenge, right? We need to find things in the universe that play out over eons. Luckily, nature's got some pretty incredible tools for the job.
Tools. Like what can outlast even the most dedicated record keeper?
Remember those repeating patterns we talked about, those natural rhythms? Well, for really long periods, one of the best tools is radioactive decay.
Radioactive decay. I mean, that sounds unstable. How's it a timekeeper?
Seems counterintuitive, but the key is consistency. Each radioactive element has a half-life, the time for half of it to decay into something else. And here's the cool part. That half-life is super consistent, like a clock that never changes its tick.
So say we've got a chunk of uranium. Its half-life is how long it takes for half of it to become not uranium anymore.
Exactly. And it doesn't matter what you do to that uranium, heat it, freeze it, shoot it into space, its half-life stays the same.
So it's like a built-in timer on a cosmic scale. That's wild. But how do we actually use this radioactive clock? Are we sitting around with stopwatches waiting for uranium atoms to poof?
Not quite. Think about carbon-14 dating. It's how we date archaeological stuff, old scrolls, fossils, you name it.
Oh, yeah. I saw a documentary about the Dead Sea Scrolls, how they use that.
Wow.
So carbon-14 is like a clock that starts ticking when something dies. Morbid, but fascinating.
Exactly. Carbon-14 is all around us, in the atmosphere. Living things absorb it, but once they die, that stops, and the carbon-14 starts decaying at its steady pace. And since we know carbon-14's half-life, about 5,730 years, we can measure how much is left in something, like a piece of wood, and calculate how long ago it was alive.
It's like a time capsule. The amount of carbon-14 is the message telling us how much time has passed. Crazy how this chaotic decay process is actually such an accurate clock. But carbon-14's got a relatively short half-life, right? What about things way older, like dinosaurs? Or even the Earth itself?
You're right. For stuff that's been around for millions, billions of years, we need longer half-lives. That's where things like uranium come in, with isotopes that last for billions of years.
Billions of years. What can we learn from those ancient radioactive clocks?
We can date incredibly old objects, like rocks, meteorites. By analyzing the uranium and what it's decayed into, we can figure out their age.
We're basically piecing together Earth's history, atom by atom, reading our planet's diary, written in radioactive decay. What does it say?
It says the Earth is about 4.5 billion years old. That's billion with a B. And that age we get from the Earth. It matches up incredibly well with the age of meteorites. Pretty strong evidence that this way of measuring huge stretches of time is accurate.
Mind-blowing. It's like the universe has this detailed diary written in slow, steady atomic decay, and we're just figuring out how to read it. But we've talked about clocks and calendars. What about those vast distances out there between stars, galaxies? How do you even wrap your head around measuring something that huge? From tiny particles to the Earth itself, it's amazing how we've cracked the code of time on these huge scales. But speaking of huge, what about those mind-boggling distances out there between stars, galaxies? How do you even begin to measure that?
You're right. Now we're talking about sizes that make the Grand Canyon look like, well, a tiny ditch. But like we did with time, we start simple and work up. Rulers, tape measures for everyday stuff. Then for a lake, a mountain, that's where triangulation comes in.
Right, triangulation. You use a baseline and two angles to get the distance, like surveyors use to map land. But I'm guessing it gets a bit trickier when you're talking at the moon, let alone another star system.
Absolutely. But the principle's surprisingly powerful, even on cosmic scales. Feynman talks about how we used it to figure out the mate of Sputnik back in '57, first artificial satellite. And even more impressive, we use it to measure the distance to the moon itself.
Wow, so high school geometry gets us to the moon, that's something. But still, compared to the universe, our planet's tiny. Using Earth as a baseline to measure a star must be like using, I don't know, a grain of sand to measure the ocean.
Great analogy. Our earthly baseline only gets us so far. But astronomers, they're clever. They found ways around this even before telescopes in space. One key was figuring out the distances between planets in our solar system, relatively speaking.
So we figured out the proportions within our cosmic neighborhood. Like, Venus is this far from the sun, Mars is that far, even if we didn't have the exact mileage.
Exactly. Imagine a map with all the streets in the right places, but no scale to tell you how long each street actually is.
But I'm guessing finding that scale, one accurate measurement, unlocks the whole thing.
Precisely. Feynman talks about how one of the first attempts at this used an asteroid, Eros.
Eros. What's special about Eros?
It's a near-Earth asteroid, meaning its orbit gets relatively close to us. Back in the early 1900s, astronomers realized they could use this.
So this asteroid was like a cosmic surveyor's mark, passing close enough to get a good measurement.
Exactly. By carefully tracking arrows from different spots on Earth during this close pass, they got a much bigger baseline for their triangulation, and that gave them a way more accurate Earth-to-Eros distance.
And with that one measurement, you could start filling in the blanks for the other planets.
Exactly. And we've gotten even more precise since, like using radar, for example.
Radar, like
Yeah.
weather radar. How does that measure the distance to another planet?
It's pretty cool. We bounce radar signals off planets like Venus and time how long it takes to come back. We know the speed of light so precisely we can calculate that distance really accurately, like a cosmic speed trap, but for catching planets.
Okay, that is seriously clever. The speed of light is our measuring tape.
Yeah.
But what about stars? Planets are practically next door compared to some of those. How do you measure distances where even the most powerful telescopes just show us pinpricks of light?
Now we're talking distances so vast, even Earth's entire orbit, millions of miles across, isn't a big enough baseline. But astronomers found another way, and it has to do with a star's color and how bright it really is.
Wait, you can tell how bright a star is just from its color. How?
It's a pattern astronomers noticed by studying stars close enough to measure with other methods. Hotter stars, they burn with more energy, right? They tend to be bluer, more luminous. Cooler stars are redder, dimmer.
So by studying the close ones, we built a kind of color brightness dictionary for stars. This color means this bright, that color means that bright.
Exactly. And here's the trick. We use that to figure out distances to stars way too far to measure directly.
Okay, let me see if I get this. A star looks dim,
Mhm.
but by its color, we know it should be way brighter. So it must be really far away, because things get dimmer the farther they are.
You got it. We compare how bright it looks to us with how bright we know it actually is based on its color. That tells us the distance. Like judging how far away a car is at night based on its headlights. If you know those headlights should be blinding, but they're just a faint glow, that car's far off.
That makes sense. It's amazing we can learn that much from just the color of the light. But what about even bigger stuff? Entire galaxies. Those are billions of stars spread out over. I can't even imagine. How do you even start measuring that?
Now you're talking scales that are truly awe-inspiring. Astronomers use a kind of cosmic ladder, each step getting them further out. One rung on that ladder is something called a globular cluster.
Globular cluster. I've seen pictures. They're like these dense balls of stars all packed together.
Perfect description. And since we assume these clusters are roughly the same size no matter where they are, how big they look to us tells us how far away they must be. We can then use those clusters to estimate distances to even bigger things, like other galaxies.
So it's like using a mountain range to judge how far away a town is. If you know the mountains are huge, but they look tiny, you know that town's miles away.
Exactly. Remember those incredibly faint galaxies Feynman described, photographed by the Palomar telescope? Using these techniques, stepping stone by stepping stone, astronomers believe some of those are billions of light years away.
Billions. We're practically looking back to the beginning of the universe. The ingenuity is incredible. We went from measuring the moon with triangles to using the colors of stars, the sizes of galaxies, all to measure distances across billions of light years. It shows you the human drive to understand this stuff is unstoppable.
It really is. And what's even more amazing is we're constantly pushing further. New tools, new techniques, all to explore the universe, from the tiniest particle to the largest cosmic structure. It makes you wonder, what other secrets are out there just waiting for us to discover them?
That's a great question, and one worth pondering. We've journeyed from billions of a second to billions of years, from the smallest particles to the edge of the observable universe. It's been an incredible journey, but like all good explorations, it leaves us with more questions than answers. What other clocks and rulers are out there, waiting to be discovered? What mind-boggling scales of time and distance have yet to reveal their secrets? We may not have all the answers, but the search itself is what makes exploring the universe so captivating. Until next time, keep questioning, keep exploring, and keep looking up.